12 volts in, 230 volts out. No transformer, no bulky windings, just a timer chip, one inductor, and a MOSFET working together to pull off this jump. Here's the schematic, and here's how it looks built up on a PCB. Now, let's step inside the circuit and see exactly how each part makes this boost happen.
At the heart of this design sits the good old NE555 timer, wired here as an astable oscillator. Its only job is to generate a continuous stream of fast switching pulses, and everything else in this circuit reacts to that pulse train. The timing network, built from a 1K resistor, a 10K resistor, and a 2.2 nanofarad capacitor, decides how fast the 555 switches. The reset pin is wired straight to the supply rail, so the chip stays permanently enabled.
Now watch what happens at the output pin of the 555. Every pulse leaving this pin travels straight along a wire to the gate of the IRF740 MOSFET, with nothing else sitting in that path. A separate 33K resistor pulls the control voltage pin of the 555 up toward the supply rail, and that same line feeds into the 547 transistor. This is where the feedback regulation happens, and we'll come back to it in a moment. The MOSFET is really the muscle of this whole circuit. Each time it switches on, current rushes from the input supply straight through a 100 microhenry inductor and down through the MOSFET to ground. During this brief on time, the inductor is not doing anything visible, but inside it, a strong magnetic field is quietly building up, storing energy. The moment the MOSFET switches off, that stored magnetic field has nowhere to go, so it collapses violently, and a sudden high voltage spike appears at the top of the inductor, right where it meets the diode. This is the classic inductive kick, and it is the real secret behind this circuit's boosting ability. That high voltage spike is caught by a fast UF4004 diode, which only allows current to flow in one direction, straight into the output capacitors. A 100 picofarad capacitor handles the fast switching ripple, while a larger 4.7 UF 230 volt capacitor smooths everything into a steady high voltage DC output. Cycle after cycle, thousands of times each second, this pulse and collapse action keeps adding a little more charge until the output climbs all the way up toward 230 volts. Of course, a boost converter without control would just keep climbing dangerously high, so this circuit includes a feedback loop to keep things in check. A 220K resistor and a 470 ohm resistor, along with a 1K preset, form a voltage divider sitting directly across the high voltage output. This divider takes a small, safe sample of that huge output voltage. That sampled voltage reaches the BC547 transistor. As the output climbs, this transistor pulls down the control voltage pin of the 555, gently adjusting the switching action to hold the boosted output steady instead of letting it run away. The 1K preset lets you fine-tune exactly where that regulation point sits, so you can dial in the precise output voltage you want. On the input side, a 470 microfarad 25-volt capacitor keeps the incoming 5 to 12-volt supply clean and ripple-free, feeding both the 555 timer and the switching stage without any voltage dips. The end result is a compact little circuit that takes a simple low-voltage battery and turns it into several hundred volts of direct current, entirely through fast switching and inductive energy storage, with no transformer anywhere in sight. One important thing before you go anywhere near this circuit: that output is high voltage direct current, and unlike AC, it does not naturally drop to zero, which makes it genuinely dangerous to touch. Always discharge the output capacitors fully before handling the board, and treat this build with the same respect you would give any high voltage equipment. Now you know exactly how 12 volts turns into 230. Try it on a breadboard. Measure carefully, and always respect the high voltage side. See you in the next one.